There's a couple of things I wanted to show you for working on some of this electrical power homework, and it has to do with resistors and how they affect circuits. So first, let's talk about some general symbols that you might run into. So if I have a line, that's just the standard symbol for a wire, an electrical wire. If I have a line with this kind of jagged line, that's a resistor. So this is a wire, that's a resistor. And resistors have some value in ohms of how much resistance they are. So for example, it might be 100 ohms. And we have a symbol for a battery, something like this. We have a slightly longer line and a slightly shorter line, and then a wire coming off of each end. It's a battery. Or some kind of voltage source. So if we put these together, here's my battery, here's some resistor attached to it. And let's say that's 10 volts. Let's say this resistor is 100 ohms. If the voltage being supplied by the battery is 10 volts, it means it's 10 volts from here to here. You always compare the voltage of something by using 2 points. So you can't just say, what is the voltage at this point? That really doesn't have meaning. What matters is, what is the voltage between these 2 points? That's equal to 10 volts. Now, because we consider wires to essentially have zero resistance, if the voltage across the battery is 10 volts, then the voltage across the resistor is also 10 volts. So my voltage across the resistor is 10. My resistance is 100 ohms. And if I know those two numbers, I can figure out the current passing through the resistor. I just divide these two values and I get 0.1 amps. So this is a simple one resistor type circuit. Next we're going to look at how circuits change when you add multiple resistors. So first let's talk about a series circuit. So we have voltage source again, battery, and this time I'm going to have two resistors. When they're connected like this from end to end, we call that a series circuit. They're connected in series. So again, let's say I have a 10 volt battery. Let's say this resistor is 100 ohms, and let's say this one's also 100 ohms. So again, if we have 10 volts across the battery, we have 10 volts from this point to this point. So I'm going to call that point A, this is point B, this is point C. So from A to C I have 10 volts, but from A to B it's less than 10 volts, and from B to C it's less than 10. In this case, because the resistors are equal, it's exactly half. So I have 5 volts across from A to B, and I have 5 volts from B to C. Now I can still determine the current passing through here because I know that through each resistor I have 5 volts and I have some current I, and I have 100 ohms. So in this case my current is equal to 0.05 amps. That's how much current is passing through this resistor. The exact same current is passing through this resistor from B to C. So the entire loop has 0.05 amps of current passing through it. So if I know that the entire loop has 0.05 amps, and I know I have 10 volts across the battery, I can figure out the total resistance. So I have 10 volts equals 0.05 amps times the total resistance. And I can solve that, and I get the total resistance is equal to 200 ohms, which is the sum of these two. So in general, when you have resistors in series, they add together. Next, we're going to look at parallel circuits. So again, I have a voltage source, my battery. I have a resistor here, and I have another resistor here. So notice it's hooked up slightly differently. I still have two resistors, but they're not hooked up end to end. The top ends are connected and the bottom ends are connected, and they're both connected to the battery. So again, if I have 10 volts, and again, let's say I have 100 ohms and 100 ohms. Now, this is a different situation from before. Here, you want to think about how the current changes. So I have some certain amount of current moving this way. Some of it goes this way, and some of it goes this way. So the current passing through this resistor plus the current passing through this resistor is equal to the current being supplied by the battery. So the current actually divides depending on the relative values of these resistors. In this case, again, because they're equal, half the current goes this way and half the current goes this way. So each resistor receives half of the current in this case. Now remember that if I have 10 volts here, I also have, so let's call this point A and point B, point C, point D. I have 10 volts across this resistor and 10 volts across this resistor. So I can figure out how much current is passing through each one. So I have 10 volts equals I times 100 amps. So, I'm sorry, 100 ohms, that's the resistor value. So my I is equal to 0.1 amps. That's how much is passing through this resistor. The exact same formula works for this resistor. So if my total current is equal to the current passing through this plus this, it's 2I, which is 0.2 amps. So here I have 0.2 amps, and again I can figure out the effective total resistance. So I have 10 volts equals 0.2 amps times RT. RT is equal to 10 divided by 0.2 gives me 50 ohms. So this is kind of interesting. Before, when I hooked the 200 ohm resistors from end to end in series, the total was 200 ohms. But when they're hooked up in parallel, the total is 50 ohms because the current splits. Don't worry about the case where the resistors are different values. You can figure out a total resistance from that, but it's not really necessary to do what we're doing in this course. You can have much more complicated resistor networks than this. I've just shown you two simple examples. The important thing to know is that when you have devices, or I've been talking about resistors, but this could be any device here, and this could be any device here. They have some load. When you have them hooked up in parallel, the current is different through each one, potentially different. And then all those currents sum up to be the current running through the battery or the voltage source. But if you have things in series, the current is constant all the way around. It's the voltage that changes. So here we have constant voltage, variable current, depending on the resistors. In series, we have constant current, variable voltage, depending on the resistors. So here's another example. let's say in this case I have an AC voltage source, 120 volts, and I have two loads attached to it. So you can kind of imagine I have two devices plugged into a wall socket. So one has a resistance of 10 ohms, the other has a resistance of 15 ohms. The question is, what is the total current being supplied from this socket? So the way to determine that, we take this voltage across this resistor here, or this device, 120 volts, 10 ohms. I can figure out the current going through that. So I simply divide 120 by 10, and I get 12 amps. This one I have 15 ohms, but the same voltage, 120 volt voltage. So I have current equals 120 over 15 is 6 amps. Scratch that, 9 amps. So here I have 12 amps passing through this device, 9 amps through this device. Therefore my total, I simply add those together and I get 21 amps. Now if I want to figure out the power being used by this circuit, this combined circuit in watts, I just multiply voltage times my total amps, and I get 120 times 21, and I get something like 2.52 kilowatts. So hopefully this will give you some hints for the homework assignment.